This is a third of three approaches to solve differential equations. The first one, recall, is an algebraic approach called initial value problems. The second one is slope fields, which is a graphical approach. And this one is called Euler's method, which is a numerical approach to solving a differential equation. So this is basically the end of the first topic. And what you have in front of you is a green curve. We don't know the equation of that curve, but let's say we were given the differential equation that represents that curve. Well, that means at a point x comma y, we would actually know the slope of the tangent line, because all we'd have to do is plug in that x comma y into that equation. And we could use that slope of the tangent line, which is essentially called dy dx, to approximate the green curve at some future value, x plus delta x, and y plus delta y. So Euler has some documentation noting this, and it's not a perfect solution, but the smaller and smaller that delta x is, the limit as delta x approaches 0, the better and better approximation we can have. Now we're not going to practically do that. We're not going to say that delta x is approaching 0. We're just going to let delta x be pretty small. Now one special thing to note is that delta y over delta x is approximately equal to, so let me change that, dy dx, when delta y and delta x are quite small. So if we let ourselves allow for some approximations, some errors in the approximation, we could save some brain power and actually come up with a curve or a collection of line segments that can approximate our actual curve. And that means at some future value, x plus delta x and y plus delta y, we can actually have that relationship. We would know what that new point is. So if we start at 1 and we want to know what y is when x is 2, then we could do 10 iterations of 0.1 or 5 iterations of 0.2. So that's the gist of Euler's method. We're basically approximating the solution to a differential equation by using linearizations based on slope of the tangent line, and delta y, delta x. This idea is best understood by just doing an example. So I'll go through an example, create a table for you, and we'll kind of go back to the picture and see what we can find out here. So the example is to use Euler's method with increments of delta x equals 0.1. So pretty small, but not so small that it's insanely difficult. And we're going to use that to approximate the value of y when x is 1.5. So we're going to basically do 5 steps. We start at 1 and we go to 1.5. Well, how do we know we started at 1? Given dy dx is x plus 1 and y equals 2 when x equals 1. Now this x equals 1 and y equals 2 is special. This is an initial value or some sort of condition. So it's sort of like the algebraic approach. We have some point we're starting with, but we're only going to numerically analyze the data. All right, so the best way to do this is to create a nice big table. And if you're working out of a document I created with you or for you, then all you have to do is fill in the headers. So I just note that we're starting at x equals 1. So I'd like you to create this table to follow along, and here are the headers, x comma y as the point that we're starting with. Dy dx is given to us as x plus 1. Delta x is staying constant the entire time, so every time it's going to be 0.1. And now something special here. I wrote that delta y is equal to dy dx times delta x. I'm going to go back to that first slide here to show you this relationship here, delta y over delta x equals dy dx. Basically, if we solve for delta y, we're multiplying by delta x on both sides. So that's why we have that relationship there. So we know delta x, but delta y is obtained from that information, dy dx times delta x. And then after we do those 2 steps there, calculating dy dx and calculating delta y, then we have a new point, x comma y. Now the end of the table here, the last column, is going to be equal to the first column here on the next row. So many times students or teachers might not write this column right here, but I write it so that it could be nice and consistent for you. Okay, so let's start with 1, 2, like the question asked. And we're going to calculate dy dx. Oh, okay, dy dx is x plus 1. So 1 plus 1, which is 2. All right, now delta x is 0.1, so therefore delta y would be 0.2. We just multiply the last two things together. And then the new point would be 1 plus 0.1, which is 1.1, and 2 plus 0.2, which is 2.2. All right, so in summary, we have that delta x, which changes that 1 to 0.1, 1.1, and then we have the delta y that changes the 2 to a 2.2. So we've moved slightly on the coordinate plane, and we have a new point, which is 1.1, 2.2. And then we repeat the process. 2.1. Now we don't need a calculator to do this. We're just moving the decimal place. So this is 0.21. And then our new point, which is 1.1 plus 0.1, 1.2. And we'll keep it to the decimal places that we obtain throughout here. So we'll go as far as we can, and then we can round at the end. So notice 2.2, add 0.21, and you get 2.41. So that point goes in the new row, and we do it again. Okay, 2.2. Now, here I'm just going to write this because I'm noticing the pattern. Okay, 2.2 times 0.1, 0.22. So the x is going up by 0.1 every time, but the delta y is changing slightly as we move. So 2.41 plus 0.22, 2.63, not too bad, we can handle it. Almost there. Second to last row, 1.3. Okay, 2.3 times 0.1, 0.23. You're probably going faster than me by now. We have 1.4 and 2.86. And that 1.4. Notice the last row on the left here. We're like, wait a second, we didn't get up to 1.5. We will. 0.24. Okay, now we have a solution, 1.5, comma, 3.10. How did I get that? 2.86 plus 0.24 must be over 3. 2.8 plus 0.2 is 3, plus another 0.06 and 0.04. Okay, I'm zooming out. I'm looking at this table of all these values, and what would be nice is to actually view this graphically. Now I'm not going to do that in this video, but notice that we could actually plot all of these points here on the right column, and you would see just very small changes in the points as we go, and it would ultimately create, the more accurate you sketch them, it would ultimately create a curve. So go back to the question. Let's see here. Approximate the value of y when x equals 1.5. So the approximate value of y when x equals 1.5 is 3.10. All right, that is an example that will work for pretty much any problem. The only unique thing that might happen is that a problem might ask for delta x being negative. So you go in the reverse direction. So the calculations are still the same. You just would start at an x value, and then you'd end up with an x value that's smaller than the original. Alrighty, thank you so much for watching. this video on Euler's method.